Before the year 1785, the study of electricity occupied a space largely devoid of the precise mathematical framework that had so elegantly defined Newtonian mechanics. While phenomena were observed and qualitative descriptions abounded, the field lacked a fundamental quantitative law akin to universal gravitation, a law that could predict and explain the forces governing electric interactions with demonstrable accuracy. Charles-Augustin de Coulomb, a name synonymous with electrostatic force, resolutely addressed this deficiency through a series of ingenious experiments meticulously documented in his treatise on determining electric force. Coulomb's ambition extended beyond mere observation. He sought to establish electrostatics on a firm quantitative foundation, mirroring the success of Newton's gravitational theory. The core problem confronting Coulomb lay in the absence of a reliable method for measuring electric forces. Existing approaches were crude, providing observations bereft of mathematical precision. Coulomb's solution emerged in the form of the torsion balance, an instrument of his own design that enabled him to quantify the minute forces between charged objects with unprecedented accuracy. The conceptual bedrock of Coulomb's works centered on his hypothesis that electric forces, like gravitational forces, obeyed an inverse square law. He postulated that the force between two charged bodies would diminish proportionally to the square of the distance separating them, a claim that demanded rigorous experimental validation. His claim was simple yet profound. The electric force existing between two-point charges is directly proportional to the product of the magnitudes at each charge and inversely proportional to the square of the distance between them. Central to Coulomb's 1785 publication are detailed descriptions and diagrams of the torsion balance apparatus. This device, a testament to Coulomb's inventive genius, consisted of a horizontal beam suspended by thin silver wire. At one end of the beam, Coulomb attached a small, charged sphere. He would then bring a second charged sphere into proximity, observing a resulting torsion. The twisting of the silver wire, the angle of torsion provided a direct measure of the electric force between the spheres, allowing Coulomb to perform quantitative measurements. To determine the force, Coulomb meticulously recorded the angle through which the wire twisted. He calculated the force required to produce this twist based on the torsional constant of the wire, a value he carefully determined by varying the distances between the charged spheres and measuring the corresponding changes in torsion. Coulomb gathered the data necessary to test his inverse square law hypothesis. The calculations were complex and laborious, demanding meticulous attention to detail to minimize potential sources of the implications of Coulomb's work resonate profoundly even in the 21st century. Coulomb's law remains a cornerstone of electrostatics and electromagnetism, forming the foundation upon which countless modern technologies rest. From the design of integrated circuits to the operation of electric motors, Coulomb's law provides an essential tool for understanding and manipulating electric forces. Its significance extends to diverse fields ranging from materials science to plasma physics. Coulomb demonstrably drew inspiration from Isaac Newton's law of universal gravitation. Newton's work served as a conceptual blueprint, demonstrating the power of mathematical reasoning to describe physical phenomena. The very idea of an inverse square law, so central to Coulomb's own investigations, echoed Newton's formulation of gravity. Newton's influence is evident in Coulomb's approach, mirroring the rigorous mathematical treatment of physical phenomena. The influence of Coulomb's 1785 treatise reverberated throughout the scientific community, attracting immediate attention from physicists and mathematicians. His quantitative approach to electrostatics provided a framework for further investigation, paving the way for the development of a comprehensive theory of electromagnetism. James Clerk Maxwell, in particular, built upon Coulomb's work, synthesizing electric and magnetic phenomena into a unified theoretical structure. Specifically, and Denis Poisson's investigations into potential theory benefited demonstrably from Coulomb's experimental work. Poisson adopted Coulomb's inverse square law to construct mathematical models describing electric potentials, thereby providing further analytical tools for understanding electrostatic phenomena. The problems addressed by Coulomb spurred mathematical innovation and theoretical development. Coulomb's meticulous experimental methodology along with quantitative results set a new standard for scientific inquiry. His work transformed electrostatics from a descriptive field into a predictive science, establishing a legacy that continues to shape our understanding of the physical world. The subsequent sections of this essay delve deeper into his experimental methodology, analyze the mathematical formulation of Coulomb's law, and explore the enduring impact of his work on the development of modern electromagnetism. Central to Coulomb's groundbreaking investigations was his ingenious invention and utilization of the torsion balance. This delicate instrument, a testament to Coulomb's inventive prowess, enabled him to precisely measure the minute forces exerted by electrical charges. The torsion balance, in its essence, comprised a slender horizontal beam suspended by a fine silver wire. At each end of this beam were affixed small pith balls, light spheres coated with a conductive material. A third pith ball, similarly charged, could be brought into proximity with one of the suspended balls, causing the beam to rotate due to electrostatic repulsion or attraction. The degree of torsion in the silver wire, precisely calibrated, served as a direct measure of the force between the charges. The precise dimensions and material properties of the torsion balance played a crucial role in its accuracy. Coulomb meticulously selected a silver wire of specific length and diameter to ensure optimal sensitivity and linearity in its response to torsion. The pith balls, carefully crafted and coated, minimized extraneous variables such as air resistance and surface charge leakage. The entire apparatus was housed within a glass enclosure to shield it from drafts and external disturbances. Coulomb faced numerous experimental challenges. Charging the spheres to a uniform and known quantity of electricity proved difficult. Leakage of charge into the surrounding environment also presented a measurement issue. Precise measurement of the distance between the charged spheres demanded accuracy in distance and angle. Despite these limitations, Coulomb's careful experimental design and meticulous data analysis enabled him to discern the fundamental relationship governing electrostatic force. His experiments revealed that the force between two-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance separating them. This relationship, now enshrined as Coulomb's law, can be expressed mathematically. F is proportional to the product of Q1 and Q2 divided by R squared, where F represents the electrostatic force, Q1 and Q2 denote the magnitudes of the two charges, and R signifies the distance between them. The proportionality can be turned into a constant using a factor K, with K dependent on the units of measurement. This seemingly simple equation encapsulates a profound truth about the nature of electricity. It demonstrates that electrostatic forces, like gravity, obey an inverse square law, implying that their influence diminishes rapidly with distance. Coulomb's law provides a cornerstone for the development of electromagnetism. It is directly related to Gauss' law, which states that the electric flux through any closed surface is proportional to the enclosed electric charge. Gauss' law offers a more general and elegant formulation of electrostatics that is particularly useful for calculating electric fields in situations with high symmetry. Further, Coulomb's law is consistent with the principle of superposition, which holds that the total electric force on a charge is equal to the sum of the forces exerted by all other charges present. Critics questioned the extent to which Coulomb had compensated for extraneous parameters. Furthermore, contemporary scientists questioned the degree at point charges were replicable. Despite these critiques, Coulomb's law found immediate application in various areas of scientific endeavor. It allowed for the quantitative calculation of electric forces in diverse systems, from simple arrangements of charged spheres to complex electrostatic devices. The design of early capacitors, for example, relied directly on Coulomb's law to optimize their charge storage capacity. Coulomb's findings served as a springboard for exploration. Poisson's work on potential theory relied heavily on Coulomb's law. Maxwell and others incorporated Coulomb's law into the broader framework of electromagnetism. Maxwell's equations, which unify electricity and magnetism, build upon Coulomb's law and extend its applicability to dynamic electromagnetic phenomena. His method and findings remain pillars of physics instruction. Coulomb's law provides a fundamental introduction to electromagnetism in introductory physics courses. The law finds application in designing circuits and modeling plasmas. Coulomb's detailed experimental approach and the mathematical precision he brought to the science of electricity profoundly shaped the landscape of physics. His work laid the groundwork for the technological revolution that would transform the world.